Hey everyone, and welcome! Today, we're going to piece together the giant puzzle of artificial intelligence. But not from some abstract theoretical point of view, no. We're going to approach this like engineers with a blueprint in hand. We're going to build an AI piece by piece, from the initial idea all the way to its real-world launch.
Because, let's be honest, we've all used AI, but what's really going on behind the scenes? What's the thought process, the code, and the strategy that actually brings one of these things to life? Well, that is exactly what we are going to break down over the next few minutes. So without any further delay, let's start at the very beginning.
Every great AI project, long before the first line of code is ever written, starts with a fundamental question. What problem are we actually trying to solve? This isn't about magic, it's about a methodical approach. And the very first step is to precisely define our battlefield.
And to define that problem, we rely on these three pillars. First, we create a model, which is just a simplified version of reality. Think of it like reducing a word problem to a simple math equation. Next, we define a clear objective. What does success actually look like? Is it minimizing transfers on a flight or miles on a road trip? And finally, we need an evaluation function. That's our ruler for measuring just how good any given solution is. Without these three, our AI would basically be navigating without a compass.
So once we know what to solve, the next big question is how? AI has evolved in its thinking strategies over the years. We're going to start with the classic methods, the ones that laid the groundwork for all artificial reasoning.
The first strategy is blind or uninformed search. The analogy here is perfect. It's like searching for your keys in a pitch-black room. You have no clues, so you have to systematically check every single corner until you find them. An AI does the same thing. It explores every possibility one by one, without any guide telling it, hey, you're getting warmer.
Now, within that blind search, there are two main tactics. Let's think about that dark room again. Breadth first search, or BFS, is like checking everything within your immediate reach first, then taking a step and checking that area, level by level. In contrast, depth first search, or DFS, is like picking one wall and following it all the way to the end before trying another. One finds the closest solution but uses more energy, the other saves energy but might take longer to find the best path.
But what if, instead of searching blindly, we could just encode an expert's knowledge into the machine? Well, that leads us to expert systems. These were one of the first huge successes in AI. Instead of exploring everything, they rely on a set of logical, if this happens, then do that rules, mimicking the decision-making process of a specialist in a very specific field.
To build this digital expert, you need four key parts. The knowledge base is its library, filled with all the rules of the game. The inference engine is the detective that reads those rules and applies them to the facts. Those facts are stored in the working memory, its personal notepad. And finally, the user interface is the door we use to talk to our detective and present the case.
Expert systems are powerful, but they require a human to program every single rule. This brings us to the next massive evolutionary leap. Systems that don't just follow rules, but actually learn the rules for themselves from data. Welcome to the era of neural networks.
It's really crucial to understand a distinction here. In traditional machine learning, algorithms learn from data, but often a human expert has to pre-process that data and pick out the most important features. Deep learning takes it a step further. It uses deep neural networks to discover those features all by itself, directly from the raw data. It's the difference between giving a chef pre-chopped ingredients versus just handing them the whole vegetable.
And right at the heart of deep learning is the neural network. It's a computational model inspired by our own brains. It's made up of interconnected nodes, or artificial neurons, all organized in layers. Each neuron gets signals, processes them, and passes the result to the next layer. It's really a mathematical emulation of how we think biological learning works.
Each artificial neuron is like a tiny judge. It receives several pieces of evidence, which are the input signals. The weights tell our judge how much importance to give each piece of evidence. The activation function is the final rule it uses to give a verdict. Guilty or not guilty, yes or no. And the bias is like a gut feeling or a personal inclination that helps the judge decide when the evidence isn't totally clear.
So, how does that adjustment actually happen? Through a really clever algorithm called backpropagation. It's a three-step process. First, the network makes a prediction. Second, it compares that prediction to the right answer and calculates the error. And here's the magic. In the third step, that error travels backward through the network, telling each little judge how to adjust its criteria so that next time the error will be just a little bit smaller. Repeat this thousands of times, and the network learns.
Okay, we've seen the theory, the logic, and the learning mechanism. Now, let's get practical. What tools do developers use to actually build these neural networks without having to code things like backpropagation from scratch every single time?
The giant in this field is TensorFlow, an open-source library from Google. It's the low-level, incredibly powerful engine that allows all these massive calculations to happen at scale. Its fundamental unit of data is the tensor, which is really just a fancy name for the multi-dimensional arrays of data that feed these models.
Now, TensorFlow can be complex, and that's why Keras exists. Think of TensorFlow as the engine of a race car, and Keras as the steering wheel and pedals. It's an interface that lets us drive that powerful engine in a simple way. Instead of building everything from scratch, Keras gives us predefined pieces, like Lego blocks, to assemble our model in just a few lines of code. That's why it's perfect for getting started and for testing ideas really fast.
And this illustrates it brilliantly. The XR problem is a classic challenge for neural networks because you can't solve it with a single straight line. With Keras, that challenge can be overcome with just about 10 lines of code. This just goes to show the power of abstraction and how incredibly fast you can test ideas.
All right, we've defined the problem, picked a strategy, built and trained the model. The final step in our blueprint is a crucial one. How do we get the world to actually use our AI? How do we connect it to an app or a web service?
Historically, applications communicated through protocols like SOAP, which were very structured and robust, but also kind of heavy. Today, the de facto standard is REST. It isn't a strict protocol, but more of an architectural style that uses the web's HTTP protocol in a very flexible and efficient way, usually exchanging data in JSON format, which is lightweight and easy to read.
And this is where a modern tool is perfect for the job, FastAPI. It's a Python web framework designed specifically to build high-performance APIs super fast. The name really says it all. It's fast to run and fast to develop with.
So why is it the perfect tool for launching our AI? First, it's performance. It's asynchronous, which means it can serve thousands of users at once without crashing. Second, it's secure. It automatically validates the data coming in, preventing unexpected errors. And maybe the best part for any developer, it generates its own interactive documentation instantly. This radically speeds up the process of getting a model from the lab into the real world.
And just like that, our blueprint is complete, from defining the problem to the strategies for reasoning and learning, all the way to the tools for building and deploying. We've built an AI, but this leaves us with the most important question of all, one that goes way beyond the code. Now that we can create these artificial minds, how do we guarantee they're used for good? How do we make them fair, transparent, and responsible? That, perhaps, is the next great frontier we all need to build. Thanks for joining me.